Okay, good morning and good afternoon, depends on where you are. And I'm very pleased to have Professor Yinxin Bian from University of Michigan as our guest webinar speaker today. And she will talk to us about a data-driven weight effect characterization. So without further ado, I will give the platform to Yinxin. And so Yinxin, you get started whenever you are ready.
Sure. So can you hear me clearly? Okay, great. Thank you so much for inviting me in this We Do Wind seminar series. So today I'm going to discuss my research on data-driven wake effect characterization. Just before presenting myself, my research includes data science, predictive modeling, and machine learning, and reliability engineering, condition monitoring, fault diagnosis. My dissertation, like a decade ago, was about operations and maintenance optimization in wind turbines. Recently, I'm working on the system optimization with digital twins and stochastic simulations, as well as the uncertainty quantification. So this presentation consists of two parts. If I do not have time, probably I can miss part two. So both are related to wake effects. The first part is the data-driven wake effect characterization for operational wind farms. So I guess the audience of this seminar knows about wake effects, so probably I don't have to really explain much about the wake effects. But basically, the wake effect stands for recirculating wind flow behind wind turbines. And here in this study, we use the data collected from an offshore wind farm, consisting of more than 30 turbines. And here, this is the rough layout. Due to the confidentiality, I didn't show the exact layout, but we modified a little bit. But this wind farm has regular positions of turbines. And here you can see that the dominant wind flow is easterly, so from west to east. And there is the one meteorology tower that collects weather conditions, including wind speed, direction, and other operational conditions. And the distance between two neighboring turbines in the direction of wind flow, so the distance between two rows is about 11 rotor diameters, and the distance in the direction orthogonal to wind flow, like this distance, is about 6 rotor diameters. And we did some exploratory data analysis. So we first, choose two turbines. As you can see, turbine A is one of the turbines in the first row, so the upstream turbine, and turbine B is one of the turbines in the last row, so the downstream turbine. And the right figure shows the scatter plot from these two turbines, and x-axis is the free flow 10-minute average wind speed measured at main mast. So this is not the wind speed measured in the cell, but wind speed measured at main mast. And y-axis is the power generation from these two turbines. And the black cross is the power from turbine A, and red circle is the power from turbine B. And of course, they kind of follow some sort of S shape, which we typically observe in turbines. So we have this power curve. However, the turbine A tend to generate more power than turbine B. So the turbine B experienced some sort of power deficits. And of course, that's due to the wake effects. And we extend this analysis to multiple turbines. And here are the power variations among these turbines in this wind farm when wind speed is around 12 meters per second. So the darker, the more power. And we normalize the power level between 0 and 1,000. And as you can see, the turbines in the first row, they generate higher level of power compared to other turbines. And second row, less. Third row, more or less. And the last row generates the least level of power. So this, turbine to turbine variations is very clear when wind speed is around 12 meters per second. Then when you look at this power variation in other wind speed, interestingly, this variation was not very clear when wind speed is low, around, let's say, 5 meters per second. This is the close to current wind speed. And also the power variation was not very clear when wind speed is high, let's say around 14 meters per second. So if you look at the left figure, the power from all these turbines around, let's say 50 and 100. So the reason is that when wind is slow, then the blades rotate slowly. So they extract like a minimum level of power energy from the wind. So the wind deficit in the downstream turbines is not really significant. So there are no clear power to power generations. Also, when wind speed is high, after the rated wind speed, then the upstream turbines use pitch control. So they don't extract the maximum level of power they can. So therefore, the downstream turbines still face incoming wind with sufficient energy to convert to the rated power. So after some wind speed, there are no clear power to power generations. And also, when wind travels from upstream turbines to downstream turbines, they can recover energy from the wind to some extent. So depending on the wind speed, we can see clear differences or unclear differences. So if we just look at these two turbines, the same turbine A and turbine B we saw here, we can see that this difference between these two turbines is clear when wind speed is in the mid-range, let's say between 10 and 12. But the difference was not really clear when wind speed is close to like a 5 or after the rated wind speed. So we want to characterize this kind of heterogeneous power deficits or heterogeneous wake effects in a multi-turbine wind farm. Also, depending on wind direction, of course, this wake effect is different. So when the wind direction, so here in this wind farm, the dominant wind direction is 225, so from west to east. Then, as you can see, in the right figure, the blue shows the average power from the turbines in each row. So under the dominant wind direction, the turbines from T1 through T9 generates more power compared to the turbines in the other rows. However, when the wind direction changes from east to west, so under the westerly wind, the turbines from T26 through T32 becomes the most upstream turbines. So you can see that they generate the highest power. So the red shows the power output under this wind direction 45, and we can see that the power generation level changes. It is, of course, a very natural phenomenon. So considering this kind of heterogeneous wake effects depending on wind speed and also wind direction, we develop a data-driven wake model for an operational wind farm using data. And we investigate how the power generation varies across individual wind farms, individual wind turbines under different wind conditions. So our goal is to characterize this power curve under this free wind flow. So mostly the power curve here, this is the incoming wind for each turbine. But here, our goal is, let's say we have free wind flow coming to wind farm, and our x-axis is the same wind flow across all the turbines, and y-axis is the power generation from individual turbines. So the turbine A, if turbine A is the upstream turbine and turbine B is downstream turbines, we will have different power curve due to the power deficit or wake effects. So here we want to construct a heterogeneous power curve of multiple turbines, which depends on wind condition. And our methodology is statistical modeling. So basically, we decompose the power output into global and spatial terms. So here you can see the black curve. This is the average pattern. So the average power curve, which is shared by all turbines in a wind farm. So this is the average pattern. But there is this, turbine to turbine variation. Upstream turbines, you see the red dashed curve above this black curve. Upstream turbines, power curve is above the average power curve, but downstream turbines power curve is below the average power curve. So there is this turbine to turbine variation, or we call spatial variation. So we want to decompose the power curve into two parts. The first one is the average pattern shared by all turbines, and the second part is the turbine to turbine variation. So here is the modeling. So the yi is the power at turbine I, and x is the weather condition or wind condition. Then we have this global pattern or average pattern shared by all turbines. And we have the turbine to turbine variation, the spatial terms. And this S function captures the heterogeneous wake effects, which depends on weather condition. So this S is not constant, but it depends on the weather condition X. So X includes like wind speed, wind direction, and also the turbulence intensity. And gamma is the coefficient of this S function. So you can think this S function is like a polynomial function or spline regression or any like regression functions. In this study, we use a spline regression for S and also G, but I think we can also use the simple polynomial regression. So basically, this spatial term depends on wind speed, because you can see that, as we discussed before, this S term is large under the mid wind speed range and small at low and high wind speed range. So this S function, the spatial term, should depend on X, should depend on weather condition. So we use this regression model as a function of X, the wind condition. And gamma I is the coefficient of the function, polynomial function or regression function. And of course, this gamma I should be different turbine by turbine. So for example, for the upstream turbines, simply gamma I should be plus, and downstream turbines, gamma I can be minus, for example, just to simply explain. So then the key is how to estimate this gamma I for each turbine. So I means the turbine ith turbine. So here, the idea is this spatial terms or the turbine to turbine variation tend to be similar for neighboring turbines, whereas they differ more significantly for turbines that are farther apart. So if we look at this, power curve, so this is estimated power curve after we apply this model. But let's look at this power curve. When wind direction is 225, then this is the estimated power curve, and you can see that the power curve from the most upstream turbine T8, the black, is this, and then T16 power curve, blue, is close to T8, and also it is close to T24, but it's different from T32. So depending on the location, the power curve changes, but our idea is these spatial terms should be similar for neighboring turbines. And so to reflect this kind of similarity and dissimilarity, we use this Gaussian Markov random field. So we formulate the interdependency or interaction among turbines using GRMF. So the idea is, so here is the coefficient of the turbine I, and this coefficient should be depend on the coefficient of neighboring turbines. So Ni is the set of neighbor turbines. So for example, let's say turbine C. Turbine C's coefficient should be dependent on the neighboring turbines. So here the red circle is the neighboring turbines. So gamma I, the gamma for turbine C, should be close to gammas in these neighboring turbines. So that is the basic idea. Then how much they should be similar or dissimilar? So here Cij, this captures the similarity. So Cij is the interaction intensity between turbine I and turbine J. And we look at, and to formulate this Cij, we look at the dependence in the direction of direction orthogonal to wind direction and also the parallel to wind direction. So we consider both wind directions, and also we consider the distance between turbine I and turbine J. Okay, so after this modeling, here is the power curve, which briefly estimate the each turbine's power curve pattern. And when wind direction changes from east to west, the T32 becomes upstream turbine and T8 becomes downstream turbine. And here the dots are all the data from these two turbines. So red is the data from T32, and you can see that red is above black in most cases, and our power curve captures this kind of heterogeneous patterns pretty well. And also you can see that this heterogeneous power deficit is very clear when wind speed is around 12, but the deficit is very small when wind speed is small and also large. So eventually we were able to characterize this heterogeneous power curve depending on wind speed and also depending on wind direction. Here is the estimated power output from one of the turbine, in this case T8, when wind speed is 12 meters per second. So in here, the darker, the more power, and also the larger the diagonal, the more power. And we can see that when wind direction, and here the numbers in the circle is the wind direction. And we can see that when wind direction is between 220 and 260, that's the dominant wind direction from west to east. In that case, T8 is the most upstream turbines, so it generates the largest level of power. But when wind direction is around, let's say 320, 340, that's the direction from north. So in that case, T8 becomes really the downstream turbine, so it generates less power. And in other case, depending on direction, its power level is different. So even though when we have same wind speed around 12 meters per second, the generated level from T8 is really different, depending on wind direction. This is the the power output from T21. So T21 is in the middle of the wind farm. So regardless of direction, it's always downstream turbine. It is affected by other neighbor turbines rotation, the blade rotation. So we can see that in all cases, it doesn't really show big differences. So for example, T8, the power level is so different depending on direction. However, T21, this is in the middle of the wind farm, so regardless of wind direction, it kind of generates like a similar level of power. And we also quantify the power deficit due to wake effects. So here, this is the power deficit across all turbines, like 30 turbines, in different wind condition, wind speed. And as we saw before, when the wind speed is about 5 meters per second, then there is no clear power, the turbine to turbine variation. And because of that, power deficit from all turbines is very small. But this power deficit, the range gets larger as wind speed increases. And when wind hits 12 meters per second, the turbine to turbine variation becomes very clear, as we saw in the middle of the lower part of the figures. So in that case, the power deficit ranges up to 21%. That means the downstream turbines can generate 21% less power compared to the upstream turbines. But as the wind speed increases further, the wake effects less intensified because because of the pitch control. So as wind speed is above rated wind speed, this range becomes smaller, and eventually when wind speed hits like a 16 meters per second, there is no really big power to power variations, and the deficit becomes really smaller. Okay, so here we compare the performance from the data from using the data from this official wind farm. We use a small number of data set, 300. So mostly this is the data from data in the dominant wind direction and sort of clean data. And power output is normalized in between 0 and 1,000. And this is the result from tenfold cross-validation. We compare our approach with global model and individual model. Global model use just one power curve for all turbines, and individual model fits power curve for individual turbines separately. And we use three metric, RMSE, MAE, and MAPE. And we can see that in all metrics, our approach was better than other models. Compared to global model, our approach produced 13 to 15% lower estimation errors. Compared to individual model, our approach's performance is not really clear because individual model also fits individual power curve. So in terms of the estimation accuracy, they should be similar. However, individual model use a lot of model. Basically, for 30 turbines, it use 30 different models. Instead, and on the contrary, our model just use one model. So even though we have similar estimation accuracy, our model is more we use a much less number of coefficients. Also, our model characterizes the interaction among turbines, whereas individual model doesn't really characterize any sort of interactions to understand the wake effects. We apply this approach to quantify so far this is the result from a couple of papers, and then we apply this approach to quantify the power gain due to the turbine upgrading or retrofitting. I understand this audience discussed this power gain due to vortex generators several times. Yeah, so so probably I guess all of you know vortex generators. I don't know the physical characteristics of VZ, but VZ is one of the way to enhance blade lift characteristics to improve the production efficiency. However, this type of upgrading or retrofitting is costly. So we met one of the utilities in Michigan, and they wanted to know whether this VZ is really helpful, beneficial to improve the power generation efficiency. And also they want to do this cost effect analysis. So they shared their data with us. Actually, the data was very noisy. So, and also they didn't really have the Met Tower. So this result is it's just to represent the benefits of our wake model, but the numbers may not be so reliable because the data was very noisy. But I want to show how our wake model can be used for retrofitting analysis. So they installed this VZ on some turbines, not all the turbines. So they have multiple turbines in a wind farm, and they install VZs on some turbines. And they have data before the VZ installation and after the VZ installation. So here is the data or the fitted power from two turbines, T30 and T31. So T30 at T30 VZ was installed, and T31 is a control turbine, so they didn't install the VZ. And in the left panel, you can see that the estimated power for this T3, and the blue is the after VZ installation, red is before the VZ installation. So you can see that after the VZ installation, the power curve is shifted upward. So there is a clear power gain, and also we can see that the power gain is quite clear when wind speed is around, let's say, 8 meters per second. So this looks good. However, when we also look at the power from T31, the right figure, also after VZ installation of T3, this T31's power efficiency also increased. So the blue after VZ installation at T3, the T31's blue power curve also shifted upward. So we believe this is this is the power curve fitting with wind speed only. But the data before and after was collected in different seasons. So we believe in addition to wind speed, other environmental factors like temperature, air density, those also influence the power efficiency. So when we quantify the power gain due to breeze installation, we thought we should also incorporate those kind of external factors. So when we quantify that, we compute the average difference on the increased power outputs after VZ upgrade, but we consider the relative difference. So here, this subscript 3 means turbine 3, where the VZ was installed. So NA is the after, B is before. So we look at the difference difference before and after the VZ installation, but we also look at the difference on the control turbines after and before VZ installation of T3. And we look at the difference of these differences. So the power gain was about like 80, average power gain was about 86 kilowatt. And when you look at the percentage, so we divide by the power before the VZ installation, the power gain percentage was about 3%. So I think this number is within the number that industry claims the power gain. But again, the data was very noisy. So, but still, our industry partners they were satisfied with this result because they see some sort of benefits when installing the VZ on their turbines. So yeah, so here is the part one. Yeah, so if you have any questions, then I can address. I'm happy to address questions before moving to part two.
So, Yunxin, a quick question. This turbine 31 is not the nearest to turbine 3, right?
This is yeah, that's a good question. So turbine 31, yeah, this is to show the relative difference. We also look at the power gain at the neighbor turbine of turbine 3. That was really interesting. Yeah, so we have turbine 3, and let's say we have turbine 4, and turbine 4 is the downstream turbine under the dominant wind direction. And interestingly, turbine 4's power gain was also clear. So the turbine 4 didn't have a VZ installation, and still after turbine 3 has this VZ installation, turbine 4's power gain was also positive compared to turbine 3. So I believe, I don't know the physical phenomena, so I look at the references, and I found that I read one article, and it says the VZ kind of stabilized the wind turbulence, so it kind of positively influenced the downstream turbines. So when VZ was installed, it not only affects that turbine, but also positively affect the immediate downstream turbine. Yeah, but here I didn't show the result because the data is quite noisy. So it's less.
Do you have an upstream turbine to compare with, for example, T5 on the other side of T3? Not a down.
I think so T3 was, yeah, if I remember correctly, T3 was the upstream turbine under the dominant wind direction.
Okay. But if you use a subset, you use a wind direction which switch the role between T3, T4.
Right.
Is that something, on that particular subset, right? What is the comparison result, right?
Yeah,
I think
right.
my feeling is the result, like you said, is interesting. It probably has a more complicated explanation. It's not necessarily
Right.
just the wake effect benefit. I mean, the VG benefit this turbine and also the neighboring turbine.
Right. Yeah. So if we have if we have reliable data, yeah, I'm happy to do that kind of analysis.
Mhm.
But yeah, we have very noisy data, and the size was not really large. Here, I just want to show how our wake effect model can be used to quantify the retrofitting influence on power gain among turbines. Yeah.
Okay.
So usually when we I don't know, I didn't really do retrofitting analysis a lot, but I believe when we do this retrofitting analysis, not only instead of just analyzing that turbine only, I think we also need to consider the wake effects among turbines in the neighborhood. So our wake effect model that consider the interaction, different interaction, heterogeneous interaction could be useful.
Okay, thank you.
Other questions? Yes.
I'm sorry, I have a question.
Sure.
So on slide, I think it was slide 14 or 15, you defined the set Ni, the nearest turbines that,
Right.
I'm sorry, maybe it was.
Yeah.
So you, to learn the parameters of each turbine, you define a set of nearest turbines, Ni.
Right. Yeah.
I'm wondering if this definition, which takes the closest turbines, for those turbines in the corner of the farm, for those turbines, you will have less number of neighbor turbines. Does
Right.
that affect the model's performance by any chance?
Yeah, that's a good question. So first of all, so the first order neighbor turbines is red, and second order includes first order and or other surrounding turbines. So when we test the accuracy between first order neighbor turbine and second order neighbor turbine, we don't really see the difference. So using just first order neighbor turbine was enough. And for the turbines in the boundary, as you said, we have less number of turbines, but still, the accuracy wasn't really deteriorated because of that, because we still have neighbor turbines like either upward or downward. So yeah, so we didn't really see some sensitive result depending on the location of turbines.
Thank you.
That's a really good question. Yep. Okay, then I can move on to the next topic. Yeah, so the next topic is the parameter calibration in physics-based wake effect model. So the data-driven wake effect model we just discussed in part 1 is useful for operating wind farms because we use the data from operating wind farms. However, this result cannot be extrapolated to other conditions like other wind farms. So we want to explore some physics-based engineering model that includes some first principles, such as Jensen's wake model or other engineering wake models. And we know those engineering wake models have been popularly used for estimating power generation levels in general wind farms. So we look at the simplest Jensen's model. Later, we use other like a more advanced wake model. But when we started this research, we first used the simplest Jensen's wake model. And here is just the core part of Jensen's model. So the Jensen's model defines the wake diameter. So how widely the wake influence in the downstream turbine. So in the graph, 0 means the location where the upstream turbine is, and downstream turbine distance, this is the distance between upstream and downstream turbine. And here in this slide, we just consider 2 turbines, one upstream and one downstream. But in our analysis, we consider multi-turbine wake model in Jensen's model. So in Jensen's model, it defines wake diameter. And also it quantifies the wind speed in wake at distance d, or s is the normalized distance, so the distance, physical distance divided by the rotor diameter. So here the wind speed in wake at the downstream turbine is defined as this. So V0 is the free flow wind speed, for example, the wind speed measured at main mast under dominant wind direction. And then there is this wind speed deficits. It has this CT thrust coefficient and the distance between upstream and downstream turbine as the normalized distance. And there is this coefficient or another parameter theta. So theta is called wake decay coefficient. But usually CT, thrust coefficient, is given by the turbine manufacturer. And for theta, in the industry or in the literature, there are some default parameters recommended. So for example, for the offshore wind farm, 0.04 is the recommended value. For land-based wind farm, 0.075 is the recommended value. And the motivation of this study is really from part one. So when we do the part one, we compare our data-driven model with Jensen's model. And we found that Jensen's models, so we use the default value of offshore wind farm 0.04, and we found that the Jensen's model output was not accurate when we use this default value of 0.04, but it becomes more accurate when you use the default value of land-based farm, so 0.075. So we thought we shouldn't use this default value in Jensen's model, but maybe we need to revisit this coefficient and calibrate or tune this coefficient using the data. So that was the motivation of this study. So then, of course, we need to see how this wake decay coefficient influence the output from wake model, in this case, Jensen's model. So this wake decay coefficient affects wind speed deficit, V1 minus V naught divided by V naught. So V naught is the free flow wind, and V1 is the incoming wind of each turbine. And here in the graph, you can see that the influence of wake decay parameter on wind speed deficit. So as the downstream distance D increases, this wind speed deficit decreases, obviously. However, depending on the coefficient value, wake decay coefficient value, this wind speed deficit changes a lot. So for example, when we use 0.1, the wind speed deficit is this red, but when you use 0.01, the deficit is this purple. So depending on value, we have very different output from Jensen's model. So so we really need to calibrate this wake decay coefficient if we want to use a Jensen's model to characterize the wake effects. Okay, so the parameter calibration, we call this one as the parameter calibration. This parameter calibration aims to improve the accuracy of computer model, in this case, Jensen's model or engineering wake model, by finding an appropriate parameter value. So we have wake model here, and we have weather condition, and we have this wake parameter theta. Then given this input condition and parameter theta, wake model generates the simulated power output. And the data from the operational wind farm, we also have data of input condition and power output. So we calibrate parameter such that the simulated wind power output can be close to the actual power output. Here we use this notation Y to denote the power output, and C, the superscript C, stands for computer model, like a Jensen's model, and P is the data from physical system, so the operating wind farm. So we want to calibrate parameter so that the simulated model is close to the actual data. So here, we formulate this problem as just an optimization problem. So the J is the J's data points and capital N is the data size. And we want to minimize the difference between the simulated output from Jensen's model and actual data. So it's very simple. And here, the Y is the vector because we have power output from multiple turbines. And because this is the nonlinear optimization, we can simply use the most popular nonlinear optimization method, which is the gradient descent. And gradient descent is the iterative way. So suppose I start with some theta, let's say theta equals 0.01. Then at every iteration, we move to different direction. So 0.01 to, let's say, 0.008, they can reduce the difference between the data and YC. So basically to reduce our objective function fk. And the direction we should move is we use the gradient. So gradient of f is the direction that increase f. And we want to minimize the loss function, so we use the negative gradient. So this is the maybe the most intuitive way to solve this problem. The problem, and this works really well for many nonlinear optimizations. Here, the problem is to evaluate this gradient, okay, gradient of f, we have to run the simulation at every data point. So we have, let's say, 10,000 data points, and each data point, we have wind speed and wind power output, 10-minute average wind speed and 10-minute average power output. And we have 10,000 data points. Then we have to run simulation or run Jensen's model 10,000 times to evaluate one gradient, which could be computationally intensive. Here, Jensen's model is not computationally heavy, but other engineering models could be more computationally heavy. And even though Jensen's model is not that heavy, if we have large operational data, this can be time-consuming. So instead of using gradient descent, which use all the data points, we can use stochastic gradient descent. And stochastic gradient descent just choose subset of data. So instead of using 10,000 data points, I will just run simulation at 1,000 data points. And I'm just randomly choose 1,000 data points and run simulation to move my theta to get the better value in the next iteration. So stochastic gradient descent becomes really popular in the era of big data, and in many deep learning, like a neural network, they use stochastic gradient descent. So this is really, the way we have to go. So here, instead of using capital N, all the data points, we just choose small n, and we compute the gradient. Okay, so we call this gradient as the gradient of f SGD. But the problem is, when we use small n, let's say just 1,000 data points, depending on which data points I choose, we will have different gradient, right? So, and the problem is, the difference between these gradients, depending on sample, could be large when we have small n. So for example, let's say gradient of L, this is the true gradient we want to go. But when we use this SGD, the sample gradient could be this or that. So when we implement this SGD, here in the right figure, this is the result. So the red is the theta over iterations. And in the beginning, it kind of converges pretty well. I think this is the numerical example. It converges pretty well. But after some points, it kind of fluctuates because the gradient really depends on sample, and it goes a little up, it goes up a little, and then goes down a little. So it doesn't really, we have to go through many number of iterations until convergence. Which is waste of time, waste of our computation. So what we do is, okay, if that's the case, why don't we control the variance of our sample gradient? So we want to reduce the variance of this sample. And there is a variance reduction technique widely used for simulation that has not been used for this SGD. So we explore this technique, and there are several types of variance reduction techniques. And here we use stratified sampling. So the idea is, in original SGD, from the big data of size n, we just choose, small n, let's say 1,000 data points out of 10,000, randomly choose. That's the original SGD. But instead of using original SGD, we divide the input data. Okay, so we divide the data with high turbulence. We divide the data with low turbulence. We have data from mid turbulence and high wind speed range, for example. So we divide the input space, and then from each cell, we draw sample randomly. So S1, for example, S1 is from first partition, S2 is the data from the second partition, so on and so forth. And we draw more samples from important partitions. Important partition means when the data varies a lot, the sample gradients varies a lot. So the fundamental idea of this variance reduction is to draw more samples from influential wind condition. In this case, it turns out that turbulence intensity is really defining factor that affects the variance. So that was the fundamental idea. So instead of randomly choosing samples, we want to choose samples. Basically, we want to choose more influential samples. So I will skip all the details, but here is the result from this SGD with stratification. As I showed before, when we do not apply this stratification, but just randomly draw samples, the sample gradient varies a lot through the iteration, so it doesn't really converge. But when we use this stratification, the blue shows that it converges within, let's say, less than 20 iterations. So we were able to solve the problem much quicker, much faster, and also use much less number of samples. So we apply this to the data. This time we use about 1,200 data points, and also we use the data under the dominant wind direction. And I didn't show how much we were able to reduce the computation. I think this audience is more is interested in the accuracy, so I just show the accuracy result. And here, this is the data from offshore wind farm, and the default value of wake decay coefficient for offshore wind farm is 0.04, but our analysis shows that this should be 0.1. So the optimally calibrated value was 0.1. And when we use 0.1, we were able to reduce the power generation estimation error by 35% compared to the default value. So we thought, we think this, the wake decay coefficients in Jensen's model and also other engineering models should be calibrated with the data to improve their accuracy of engineering model. So here is the result for the Jensen's model, but later we also implement our approach in other wake model, such as Gaussian wake model. And now we are extending this approach for functional calibration, where the parameter is a function of weather variable. So here, this case, the same data, wake decay coefficient. And maybe this when we use this wake decay coefficient as a function of weather condition, like wind speed and direction, we may have enhanced the result. So we are considering functional calibration. We are also working on dynamic calibration, where the theta changes over time. So this is the approaches we are currently pursuing in our research group. So in summary, in part 1, we present a data-driven wake model where heterogeneous wake effects are quantified in a multi-beam wind farm. In part 2, we discuss new stochastic optimization model to calibrate the wake effect in engineering models. And we believe these approaches can be useful for some decision-making applications, such as wind farm layout, design, and control, as well as the retrofitting analysis, as we discussed. So you can find some related publications. And also, I posted the data and code on the GitHub page. So if you are interested, then you can visit this GitHub page or my website to get more information. Thank you so much.
Well, thank you, Yinxin, especially for sharing your data. I think that's very important, and for other people to try on your method, and also they could possibly use the data for something else, right? So we have 10 minutes left. Any questions from the audience?
Yeah, thanks. I just one question. Thank you very much, first of all, for the fascinating talk, and it's really interesting to see how you were using this very valuable resource of the data to tune the model. I just was wondering if you ever considered splitting the data into different atmospheric conditions, stable atmosphere versus unstable atmosphere, to see whether you saw different wake decay parameters for those different atmospheric conditions when you fitted it.
Right. Yeah, that's a good question. I think we in recent paper in this second last paper applied energy, which was published in applied energy, we consider different stability condition, and we calibrate parameters depend. So we divide the data when the condition is stable, unstable, and we calibrate parameters differently. I don't remember the result on top of my head, but yeah, we had some analysis depending on the stability. Yeah.
Thank you very much. Thank you.
Anyone else? So, Inja, I have a question for the stochastic gradient descent. Do you think, I suppose you coded your own stochastic gradient descent yourself, right? Your team did that. You
The
didn't really
code program, the stochastic gradient descent?
Yeah, you didn't really use any kind of existing package, did you?
Right. We coded by ourselves.
Yourself. Okay. Is possible some of the existing package can be used or their method can be used? For example, Atom, which is widely used in deep learning stochastic gradient descent.
That's a good question. So I guess of course, my student program, so maybe I'm wrong. But what I understand is to use the existing package, you have to put the function in the package, right? But our problem is our function. This is not closed form. So for example, YJC. So YJ is the data, so we have number. But YJC is the function. But YJC is not the closed function. Let's say AX squared plus BX plus C, for example. But this is to evaluate this function, we have to run Jensen's model. So we have to call Jensen's model. So my guess is we cannot use the existing nonlinear optimization package.
I see. Another question is about the coefficient in the Jensen's model you estimate, right, from 0.04 to 0.1, which is quite substantially different on the surface. So what do you think the existing Jensen's model or whatever the guideline they suggested for offshore wind farm is because of this number was obtained many years ago, nobody really kind of cared to update it afterwards. It's on the old turbine, new turbine is different and so forth, or is because of something else? You might not have an answer. I just thought, ask you just in case you have something to share.
Right. So yeah, that's a really insightful comment. So I think this the recommended value was from decades ago, maybe several decades ago. I don't know. So
7
this
decades
value,
ago. Okay.
yeah, because Jensen's model I think was devised in 1980s. So first, so I believe that time people may not have big data, the data from many operational wind farms.
The turbines are different too, right?
Yeah, right. Turbines are different too. Yeah. So I believe we have to revisit this coefficients and see what should be the value from each farm. And if we can kind of relate the optimal value with the farm characteristic, like offshore, onshore, or terrain, then we may have better idea. Yeah, if the terrain is irregular and this type, the coefficient should be this value, or this value is better than the old one. So yeah, if the data from different wind farms are available, I'm very interested in looking at those issues. Yeah.
But you didn't find any updated recommended value in the literature, right?
Yeah, there are some few papers that try to calibrate this, but those papers are also, you know, just from limited wind farm data. So we cannot really say this can be applied to, you know, other wind farms in general.
Okay.
Mhm.
Any other questions from the audience? We have about 3 minutes left.
I have a follow-up question,
Please,
what you
please.
have been discussing. Did you use like the whole year of data, or I mean, even that there's a subset, do you think it is representative for a year, or maybe
Yeah, that's
more
a
like
good-
a season?
Yeah, so this is from multiple years of data, but we use the data when wind direction is the dominant wind direction. So you can see wind flow here. So this is not the data from 1 year, but from multiple years. Just use the data in this narrow wind direction.
Okay,
Yeah.
thank you.
It's 10 minutes, right?
10 minutes, right, right. And in this analysis, we just use 1,000 data points, but later we extend to larger data sets. And,
Okay,
and I think that's a good question. So maybe I don't know, maybe this coefficient evolve over time because turbines deteriorate and operating conditions change over time. So maybe this coefficient 0.1 is optimal at one point, but later it should be adjusted a little bit. That's why we are working on the dynamic calibration and also the functional calibration. But then really needs large number of data collected over time.
Okay. Well, thank you very much, Yinxin, for sharing your research with this group. Just do a little kind of advertisement for the next 2 months, and on October 13th, we're gonna have a Mario De Floro from Unreal to talk about the physics informs machine learning and with its application to wind energy. And then November 10th, and Dr. Jen Tao from Texas A&M University will talk about digital twin and with its application to wind turbine maintenance. And his digital twin is more like a movie type of digital twin. It's probably a little bit different from some of the digital twin we talk about the model-wise. Okay, and that pretty much conclude our today's webinar, and I appreciate all for coming, and we'll request the slide stack from Professor Bian afterwards, and also put the recording under the usual place. Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.
Fine. Thank you very much. Thanks.